Welcome to The Explainer. So today we're looking at something that is kinda hidden in plain sight, but is actually an absolutely vital, highly sophisticated marvel of modern engineering. We're talking about the offshore wellhead. You know, when you look at a massive offshore platform, your eyes are immediately drawn to the giant derrick, right? Or the helipad, or those sprawling processing modules that look like a small city on the water. But beneath all of that, holding the entire megastructure's primary function together is an unseen hero. It's a component that bears just unimaginable weight and holds back extreme geological forces. Without it, the whole operation literally wouldn't exist. So let's peel back the steel in the ocean water and see exactly what makes this hidden skeleton so remarkable.
Okay, let's dive into this by making a really crucial distinction. In the world of offshore engineering, you'll hear the term Christmas tree a lot. Now, if the Christmas tree is the brain of a well, the highly visible control point with all its valves and sensors directing the flow of oil and gas, then the wellhead is its skeleton. It's the unsung, heavy-lifting, weight-bearing backbone. The tree definitely gets all the glory for operating the well, but it's the wellhead, sitting just below it, that provides the true structural foundation. It takes on the monumental task of supporting the enormous, crushing weight of everything suspended beneath it.
All right, part one, the wellhead skeleton. Let's look at how it holds it all together. The wellhead's primary job is quite literally to hold everything together. An oil well isn't just a single simple hole in the ground. Actually, scratch that. It's more like a complex, multi-layered structure of steel pipes extending thousands of meters down into the earth. Sitting right at the top of the conductor pipe, just above the drill floor, the wellhead acts as this master foundation. Hanging straight down from this one single assembly are multiple casing strings. These are progressively smaller steel pipes extending deep beneath the drill floor. Everything suspended down in the earth is ultimately supported right here at this specific point.
Moving on to part two, concentric housings and hangars, nested just like Russian dolls.
Now, what's really interesting about how this is built is how engineers actually achieved this suspension. Think about Russian nesting dolls. It's honestly the perfect analogy here. Just like those wooden dolls that fit perfectly inside one another, a wellhead is built using a series of concentric, nested components. The outermost shell, which we call the conductor housing, is welded directly to the top of the massive conductor pipe. Then, inside of that, each successive casing string that goes deeper into the earth hangs from its very own hanger within the previous housing. It's this beautifully modular system where every single new pipe gets its own secure resting place.
Let's zoom in on one of those resting places for a second. The casing hanger. This isn't just some simple everyday hook. It is a highly precision-machined steel mandrel. And notice its specific profile. It's engineered to perfectly match a landing shoulder that's machined inside the wellhead housing. When thousands of meters of heavy pipe are lowered into the well, this relatively small, specific piece of steel is what actually catches them and holds them securely in place.
Imagine the process of actually making this happen out on a rig. It is a massive, heavy-duty operation. First up, the drill crew runs the casing string into the well, joint by joint, literally threading 9-meter lengths of steel pipe together until the whole thing is thousands of meters long. Then, as the final joint goes in, the casing hanger that's attached to the top finally lands. It comes down and rests perfectly on that landing shoulder inside the wellhead housing we just talked about. The entire weight is transferred, and finally, the critical annular seals are installed to lock it all in and make it completely pressure tight. So you're left with a permanent suspension system installed under extreme, high-stakes conditions.
Which brings us to part three, supporting massive casing weights. And trust me, the forces here are mind-boggling.
So the crucial point here is that when we talk about supporting weight, we are dealing with forces that are just hard to wrap your head around. Consider this number, 92,000 pounds. That's about 41 tons. That is the physical weight of just one single 4,000-meter casing string of standard 7-inch pipe, assuming a common spec of 23 pounds per foot. Imagine 41 tons hanging entirely from that small steel shoulder we just looked at. And remember our Russian nesting doll analogy from earlier? The wellhead doesn't just support one string, it has to support multiple nested strings like this, totaling hundreds of tons of dead weight, all pulling down on that single solitary assembly. No pressure, right?
Part four, critical annular seals, creating the impenetrable fortress.
Well, it turns out supporting all that immense weight of the steel is really only half the battle. The wellhead also must act as an absolutely impenetrable fortress against extreme geological pressures, and it does this using annular seals. These are high-integrity, typically metal-to-metal, barriers that are installed directly between the casing hanger and the wellhead housing. Their job is to seal off the annulus, which is the empty space between the nested pipes. Because think about it, if these seals fail, high-pressure hydrocarbons could migrate upwards between the casing strings. That leads to fluid escaping into other formations, or worst-case scenario, making its way right up to the surface. It would completely, utterly compromise the entire well's integrity. It's literally a barrier between safety and catastrophe.
Part 5. The Wellhead Integrity Test. How engineers guarantee safety.
Because the stakes are so incredibly high, engineers absolutely do not leave anything to chance here. They have to guarantee, without a shadow of a doubt, that every single critical seal is undeniably secure before that well ever goes live. So they do this through a rigorous wellhead integrity test. This process happens before the Christmas tree, the brain of the well, is ever even installed. The engineers will apply intense artificial pressure to each annular space, one by one. And those metal-to-metal seals, they must hold this pressure perfectly for a strictly defined period of time. This physically proves that the barriers can withstand the intense, real-world pressures of the reservoir once things get flowing.
Let's move to Part 6, Subsea Wellhead Applications, and see how this builds when we adapt it for the deep.
So, pretty much everything we've discussed so far applies to surface wellheads, the ones sitting on massive steel structures right above the waves. But as the industry pushes further into deeper waters, this exact same skeletal foundation has had to be adapted for the dark, high-pressure depths of the ocean floor. Now, while the subsea configuration definitely looks different than a surface setup visually, a subsea wellhead follows the exact same mechanical principles. It still uses those concentric housings, the hangers, and those crucial metal-to-metal seals. The major difference? It is installed entirely from a floating drilling rig and operated remotely by robotic ROVs, thousands of feet underwater. It's the same reliable skeleton, just surviving and functioning in an alien environment.
Once all the drilling is finally complete and those casings are hung and cemented into place, we reach the final subsea configuration. You're basically left with a massive steel wellhead housing jutting right out of the seabed, featuring a lockdown sleeve or a specific structural profile. It just sits there, securely holding hundreds of tons of steel and isolating immense geologic pressures, patiently waiting and ready to accept its brain, the subsea Christmas tree, which will eventually be lowered down to connect right there on the ocean floor to complete the whole shebang.
It really changes your perspective on the whole operation, doesn't it? The visible machinery up top is definitely impressive, but the unseen engineering making it all possible is just nothing short of miraculous. So, the next time you see an offshore platform on the horizon, or you're reading about a new deepwater drilling operation, ask yourself, what's holding it all together down below the surface? Remember those concentric housings, the massive weights resting on tiny precision machined steel shoulders, and the unbreakable seals of that unseen skeleton. Thank you so much for joining me on this explainer today. Keep learning, keep questioning how things work, and I'll catch you in the next one.